So we'll be proving these two identities. So the first is that the product from r equal to 1 till n minus 1 of sine of r pi upon n, that is n upon 2 power n minus 1. So it basically sine of pi upon n, sine of 2 pi upon n, sine of 3 pi upon n, all the way till sine of n minus 1 pi upon n, that will be n upon 2 power n minus 1. So this involves complex numbers. First of all, read those and get familiar with those, because yes, it will involve a lot of that. So we can write sine theta as e power I theta minus e power negative I theta upon 2i, which can be written as I e power negative I theta upon 2 into 1 minus e power 2i theta. So it's just basic algebra right now. Then this product can be written like this. So the first thing that's outside of the bracket, that being producted, yes, and then the thing inside the bracket, that in the product. Now this first bracket is very doable, so this is very much easy. Yeah, right. But for this bracket you need something else. So we know that we can write x power n as the product of its factors, and that is basically just x minus a 0 and then the product of all such terms. So x minus the first 0, x minus the second 0. Well, of course the first obvious 0 is 1, but then there are the complex roots of unity. You can use those as well, and yes, you can write this thing as x minus 1 into x minus e power I 2 pi upon n, and then x minus e power I 2 pi upon n times 2, and so on. So there will be exactly n of these zeros, right? But then x minus 1, we will kill that by dividing by x minus 1. So basically we just get another identity, and x power n minus 1 upon x minus 1, using the GP formula, we can write this thing as 1 plus x squared till x power n minus 1, right? And that's this thing, this summation, and that's equal to product from r equal to 1 till n minus 1, because r equal to 0 was 1 minus x, sorry, x minus 1, and that was gone, right? So now it's just x minus e power I 2 pi upon n r, that in the product from 1 to n minus 1. The next step is just to put x equal to 1, because this is an identity. You can just put x equal to 1. Now you might be thinking, well, we divided by x minus 1 over here, so why can we do that? Shouldn't this give us something that is not correct? Well, it does give us something that is correct, because the thing is that this is more fundamental than this, right? So we just have the product from r equal to 1 to n minus 1 of 1 minus e power I 2 pi upon n times r. That is the summation from r equal to 0 to n minus 1 of 1, which is basically n, right? So the left hand side, that thing is on the right side now. So we are putting x equal to 1. So it's just 1 plus 1 plus 1. How many? N times 0 to n minus 1, there is n of these. So n. And then this product is exactly what we have been looking for. So that means this thing is indeed n upon 2 power n minus 1. Let's go to the second identity. So it's this thing. Summation from r equal to 0 to n minus 1 of tan square r pi upon n is 2 power n, sorry, it's not to the power of n, it is 2 times of nc2, so n choose 2, right? Yes, and you can clearly see that n should not be even. If it is even, then this will in fact contain tan square of pi upon 2, which is very problematic, right? Because that is not defined. So n must be odd, and if it is odd, then this identity is true. So in our assumptions, we have n is odd, and we will denote tan of pi r upon n as tr, and then once again, just using Euler's theorem, you can write e power I 2 pi r upon n as 1 plus I tr upon 1 minus I tr. Then just send that to the left hand side, and then raise these to the power of n on both sides. So this thing e power I 2 pi r upon n, that to the power of n, that would just be 1, because e power I 2 pi r, right? And r is an integer, of course. So this just becomes 1 minus I tr to the power of n is equal to 1 plus I tr to the power of n. Then using the binomial theorem, we can write this kind of equation. and then we define a function. So we take this polynomial function, so it's the summation from k equal to 0 to n of nc k I power k minus I power negative k. How is that happening? So negative I is just 1 upon I, and that's why I power negative k, and then x power k. So this thing is a degree n polynomial, because yes, when you put n in there it becomes x power n, and I power n minus I power negative n, that is not 0, n is an odd number. So this is a degree n polynomial in TR. Well, okay, it's not in TR, in fact it's in X now, but originally we used TR, so this was technically in TR, but we can also use X. So this is a degree n polynomial in X, and it has zeros TR, right? So each TR value actually satisfies this. So TR, that just represents T0, T1, T2, T3, Tn minus 1, all of them. So now we know all the n zeros of this thing. We know there's not going to be any more of them, right? Because it's nth degree. And all of these are of course distinct. Yes. So then we can use a polynomial theorem that says that the summation of these zeros, that's just the coefficient of the second leading term, negative of that upon the quotient of the first leading term, and you know all of those other summations as well. Those are very popular. I don't have to explain them. So we can use this summation and this summation, and we can just get these values from this polynomial itself. So this summation is in fact very easy, because I power n minus 1 minus I power 1 minus n, that's just 0. Why? Because n minus 1 is an even number. So I power n minus 1 is negative 1 to some integer power, and this thing is 1 upon negative 1 to the same integer power. So both are in fact the same thing, and that means this is basically, this bracket is just 0. So this whole summation is 0. Cool. And then summation of Ti Tj. So this summation is for all values of I and j that you can get, and it should be such that I is not equal to j, and also there should not be a repetition in there. So Ti Tj and Tj Ti, those are not distinct, right? So you cannot have T1 T2 and T2 T1 both in the summation, right? There's only going to be one of them. That means one repetition only, right? You get the idea, because this is used a lot everywhere, so this must be very popular, right? So this can be written as nc n minus 2 upon ncn, so from this polynomials coefficients and the other things over there as well, right? Because those are also in the coefficient. Right, now the good part is that I power n minus 2 minus I power 2 minus n, this thing is not 0. Instead it's the same thing as I power n minus I power negative n, in fact negative of that thing, because I power 2 is negative 1, right? So write this thing as I power n into I power negative 2, and I power negative 2 is just negative 1. Similarly this thing is just I power 2 into I power negative n, so that's just negative 1 of I power negative n, and then take that negative 1 out. So this thing just turns out to be negative nc2, and from that this quickly follows. This is very easy to prove. So the thing is that the sum of some terms is 0. We know what the sum of their pairwise products is. So then the sum of their squares is just negative 2 times this sum, and that will be exactly 2 nc2. Cool. So this is it. I'll see you guys in the next video. Bye.